So, hello everyone. As you've heard, my name is Florian Müller. I'm from the Technical University of Darmstadt, and I present some work from my colleague Martin Schmitz, who unfortunately cannot be here. However, I'll try my very best. So, I present you Capricate, a fabrication pipeline to design and 3D print capacitive touch sensors for interactive objects. So, okay, what are we talking about? We're talking about 3D printing, and 3D printing allows us to create a multitude of custom-designed objects. However, what comes out of the printer normally is just a dead plastic object. So what we're about to do is we're considering the question how we can make those objects interactive. And if I say interactive, I mean touch sensitive for this talk. So in the related work, there are mainly two approaches on how you can do that. The first one is using external augmentation, which means using depth cameras or some external tracking tools to recognize touch events on 3D printed objects. The second approach is post-assembly, which means we first print the 3D object and then use some conductive tapes or foils or something else that we attach to the object after printing. Those approaches work good for flat and ruled objects. However, they might have problems and require maybe a complex setup that is fine in a lab environment, but might be hard to do at home. And they might have also problems on doubly curved objects. To overcome those issues, we come to contribute Capricate. So what's Capricate? Capricate is a fabrication pipeline that reaches from the 3D model on the PC all the way through to the other side, having some printed interactive object and having example applications for that. On that way, we contribute parts for every step. First step is designing interactivity. Here we contribute an easy-to-use design environment, as well as touch sensing techniques that work on doubly curved objects. In the next step, the actual 3D printing, we contribute practical guidelines as well as some technical evaluations that I'm going to talk in a few minutes about. And the last step, after we have printed the interactive objects, we provide example applications on how you can use such objects as standalone devices as well as on-screen tangibles. Okay, first step, designing interactivity. For the designing interactivity part, we mainly have three parts here: designing, wiring, and generating. Let's first have a look at designing. I have a video of that for you. So what you see here is a regular 3D model that we downloaded from the internet and loaded into our tool. What you see is the user placing a touch button on the object and then fine-graining his selection. After he placed that button, he can also do multiple buttons. We'll see that later. And after the user is finished with that, the magic happens, and our tool does the wiring throughout the model based on a star algorithm, and then generates fabrication files that you can use with off-the-shelf 3D printers that have two extrusion heads. While this is pretty easy for one button that you've seen right now, the question is how can we do this for touch grids on doubly curved objects? A more complex object might look like this, and if we want to have a touch grid on it, we have two possible techniques in the paper. The first is curved surface touch. The idea behind curved surface touch is basically that we have touch electrodes that follow the geometry of the surface of the object. How we do that? Basically, the user selects a region, and after that, our system uniformly distributes touch points in this region, and in the second step uses a Dijkstra-based region drawing algorithm starting from each of the touch points to fill the regions. This works quite well on every custom-shaped object. However, the result is pretty time-consuming to print with today's printers because the printer has to change the filament pretty often. To overcome this, we propose a second solution, which is flat surface touch, where we position, as you can see on the picture, the touch electrodes only on the bottom of the object and not throughout the whole object. The question here is, how can we then sense touch? Because there is different amounts of material on top of the touch electrodes. The naive approach would be to use one threshold for all touch electrodes, but this might result in no, or on the other hand, too early detection, depending on how much overlay you have over the touch electrodes. So what we provide here is the idea that we have the actual 3D model, so we know the amount of material that will end up on top of the electrode. So we use this information to calibrate the threshold per electrode. So how do we do that? We evaluated the effect of the PLA overlay thickness on the sensing performance, and this resulted in the material function that you see on the slide. So you see on the one axis the overlay thickness and the SNR on the other axis. And what we then do is for each electrode, we compute from the 3D model the overlay thickness above this electrode, then evaluate the material function that you see here for this thickness, and in the last step, we adjust the threshold according to this value. Okay, that's for the designing interactivity step. In the next step, the actual 3D printing. As I said before, we use completely off-the-shelf hardware. This is a Ultimaker printer with a dual extrusion head, and we use regular filament, and we use a conductive carbon-based ABS filament that's also commercially available as it is. So while printing, we observed that the conductivity of the printed circuits greatly influences the sensing performance. And we found that the way how we print those circuits also influences the conductivity. So we tested two different ways of printing them, printing the circuits, perpendicular printed or line printed with a current flow. And we found significant differences. And we found that the stripes that are printed aligned to the current flow are about twice as conductive as perpendicular printed stripes. So as a conclusion for that, if you want to print conductive traces, then print them alongside the direction of the electrical flow. Right. After we have printed those objects, we want to do something with it. So we here have some example applications that we think some prototyping like this might be helpful for. One is physical input devices, where you can prototype physical input devices that you want to try out, and this works pretty fast with this technique. Second part is wearable computing devices because wearable devices are something that you customize to the user, and there this technique might be very helpful. And the last part here are printed tangible UIs, like this mountain that you see here. Maybe some of you have also seen it in the demo yesterday, if you've been there, that you can use to interactively explore 3D data, or on the right bottom side, a steering cross that you can just attach to your mobile phone and use it as a control for a mobile game. Okay, I presented you Capricate, a novel way to make 3D printed objects interactive. Capricate provides a simple design tool, works on doubly curved surfaces, and works with off-the-shelf printers and materials. So, thank you.
Okay, great. All right. So this is the last talk in the session, so we can spend the rest of the day with questions if you like to. Look around. All right, there's the first question. Paul Dietz in the back.
So I could imagine this being very helpful. It's very cool. Nice work. One thing that is a common problem in capacitive sensing systems is people forget that the entire length of wire is all sensor as well. And so often it's useful if you don't, particularly if you have a small sensing area that you want to actively shield the, that wire going up with. And it seems to me that this tool could be extended fairly easily to make that an easy operation. Is that something you've considered?
Well, as you've heard in the beginning, I'm not the actual author, and I'm really not part of this project, so I can only speculate here.
But you can certainly, I think Paul has a really good idea, and it's probably
yeah,
just...
of course, this is a very good idea, and I can forward it to Martin.
Here's a proxy here, here's a proxy.
Yeah,
there you go. All right, more suggestions to the authors. All right, we have a question in the second row here in the front.
So also another suggestion is that I think it's really nice to see you did the characterization of the anisotropic conductivity based on the trace, how you print it. I think that's super interesting. It would be nice to see more exploration on that side, because it's really taking the disadvantage of FDM but turning to that advantage. It's really nice.
Okay, thank you. I'll forward it.